All right. So, first question here. It says that Tara really wants to win lunch with Miss Shero. Who wouldn't? What's the smallest number of degrees that she can spin in order to win? So we want to sketch the angle here on the axis. So I want to point out in our directions here that one of the guidelines was that if we land on a line, we can actually pick either one of the two sectors that we land in. And so if we take a look at the sector for lunch with Miss Shero, and we want to try to find the smallest number of degrees that will get us there, we can actually say 150 degrees. So that's the closest line that's going to allow us to then pick that as an option. If you put 180 degrees, yeah, that would still get you lunch with Miss Shero, but it's more than the least possible option of 150. I had a couple people here say 151 degrees, just thinking it has to actually be in the sector, but it turns out it's okay if it is just on the line. So here's how we're going to go ahead and label that here. When you're drawing an angle, there's three things that I want you to include in your picture. We're going to start by drawing our starting position. I can draw that a little bit straighter. And that's just matching like what we said up here at the start. Like that has to be the starting position of our paperclip. And then we're going to go ahead and draw the line that kind of shows, we're just going to kind of estimate where that would be close to the 150 degree mark. I'm going to label that position as 150 degrees. And then the last thing I want you to include is a little arrow like this, and that's showing us the direction of the rotation. So it's showing us that we're going in the counterclockwise direction. All right, we are going to put a few labels here onto the picture. So go ahead and switch to your different color. And we're going to actually label the starting position of that paperclip is called the initial side. And then we also have a name for the other line where our angle is ending. So the line where we labeled the 150, we're going to call this one the terminal side. That's where our angle measure ends. And so this type of picture here that starts with the initial side, exactly where we place ours, it's showing the terminal side, it's showing the little arrow, showing what direction we're going. Generally, we call this an angle that's drawn in standard position. Whoa, that's not so big. So if you see something that says draw this in standard position, it's important that you have your initial side here. Now your terminal side could be somewhere else. Depending on what the angle is, really the terminal side could be anywhere in our circle, but the initial side is always where it is here. And those are our requirements there for standard position. Okay, so we're going to go back to our spinner here, and we're going to see what actually happened here in part 2. It says that Tara actually spun 510 degrees. Did she win lunch with Miss Shero? Some people say no, some people are saying yes. How can we tell? What is it that we're looking at? Go ahead, DJ. Yeah. I actually intentionally stopped at 480 because I wanted you all to think about how we would continue labeling. But it turns out that if we just continue adding 30 each time, notice that 510 is another label for the same position. It has the same terminal side as 150. And so what that spin would look like is starting here, we've actually gone one full time around the circle, that's 360, and then our paperclip is not stopping yet, it's still going, and then it ends on this line. And because we're still on a line that's touching the option of lunch with Miss Shero, that could still be an option to win. So I'm just going to make a note here that Tara just went one more time around the circle. Around the center. Let's say that. And so we're going to make a slight adjustment of drawing our angle here on the axis. So we're still going to have our initial side in the same place. The terminal side is in roughly the same place. What's going to change is the little arrow here that we drew to show the direction that we're moving. Right here, we are going to start at that initial side. We're going counterclockwise. It's going to go one full time around, and then we're going to keep going all the way until we get to that terminal side. So it's going to kind of make a little bit of a spiral look. That's how we know that we've gone around our circle more than once. And let's go ahead and label this picture here. So that's representing the angle 510 degrees. Now, in parentheses here, I'm actually going to label the old name for that same location we saw initially, that it was also the same as 150 degrees, or at least it had the same terminal side. And so there's actually a special connection between these two labels. And here's how we can start to think about that. If we were to begin at the terminal side, so pretend like I've got my paper clip going across this line here. And if I were to travel one full time around the circle and end at exactly the same terminal side, how many degrees did I just travel? Yeah. So look at this. So if we started with 150, if we do 150 plus 360, we get 510. So let's make note of that off to the side here. So the connection between our two angles, what actually happened is we had our original label of 150. We're adding 360 because we're just thinking about going around our circle one more time, and that actually gave us the other label of 510. And this is just a coincidence here that they both happen to have a 1 and a 5 involved. That's not always going to be the case. So the special name that we have for these two angles that have the same terminal side, they are called co-terminal angles, because the terminal side they have here is the same. So we're going to make a note of that off to the side here in the margin, that what number 2 is showing us, it's showing us an example of co-terminal angles. And it's really easy to find co-terminal angles. Whatever your original angle measure is, you can add 360 degrees, which is just what we did here. Or you could subtract 360 degrees if you wanted to go the other direction. So think about this. If we were to start with 510 and then subtract 360, it's going to get us back to 150. Now, this process of finding co-terminal angles can actually continue on and on in either direction. So let me show you what that would look like here on the calculator. So starting with that angle of 150, we can add one revolution of the circle, and we get 510. Well, we could actually add 360 again to get another coterminal angle, which is 870. If we add it again, we get another coterminal angle, 1230. We could add it again, we could add it again, and you get the idea here. We have a lot of possible labels for that location. Now, it also works going backwards. Okay, so let's say that we started with 150. We could subtract 360. That's actually going to get us to a negative angle label. We're going to talk more about the negative angles here in just a moment. But notice here that we could keep subtracting 360 to get lots and lots of coterminal angles for that location. So actually there's really an infinite number of angles that are coterminal to 150 degrees. So you can add or subtract 360 on and on forever. Okay, so let's look at the rule breaker in part 3. Reed broke the rules. Well, he wasn't listening, and he's spun clockwise instead. he actually spun 35 degrees clockwise from the starting position. So, where's my spinner? Let's see if we can try to maybe label that. So if our starting position, I'm going to use a different color here. All right, so we're still starting in the same position here, but he went 35 degrees backwards. So going clockwise is now going this way. And how many degrees would it be to get to this first line? It's 30, and so, but his is 35. So it's just going to be a little bit past that first line. So he's in the sector of extra homework, which kind of makes sense, because if you don't listen, give you some extra homework to do. And so the way, though, that we would label that arrow, we would label it going backwards. And really the distance here, the degrees that we traveled through, is just 35 degrees. So I'm going to go ahead and label that back on this picture here. So the first angle, the one from Reed, ends up looking something like this. Now, all of our spins, all of our angles up until this point, they've always gone in the counterclockwise direction. And notice that we label them with a positive angle. So what could we do to label the 35 degrees here that we actually traveled going the other way? That's what's going to be negative. So let's write off to the side here, this is actually going to be negative 35 degrees. The negative sign is telling us that we went clockwise. 35 degrees is still just the actual measure of the angle. Now, it says here that Nick followed the rules, and he landed in the exact same spot as Reed. So if I were to switch to another color here, maybe green, to show Nick's, he landed in the same spot, but he followed the rules, meaning he traveled in the correct direction, which was counterclockwise. How many degrees, or what's the smallest number of degrees that Nick could have spun? So let's go ahead and label that here. And Jacob, how did you get 325?
I added 360 degrees to the negative 35.
Yeah, so that's one way to think about it. So starting with the negative 35 label, really what it is it's finding a coterminal angle again. That if we were to add 360 degrees here, it's going to be starting at this position. We're just going to go one full time around the circle. We're going to end up where we started, but now we have a positive version of that angle. And if we know that one full time is always got to be 360, it makes sense because 325 plus 35, if we just look at the size of the angles, they together would have to add up to 360. So here we actually have another set of coterminal angles. So we could have done our calculation in the opposite direction. If we started with 325 degrees, notice that if we subtract 360, that's going to get us to negative 35. Okay, but the big thing that I wanted you to see here on this part is just what gets us a negative angle. So let's make a note off to the side here that if we go in the clockwise direction, it results in a negative angle. The other option, if we follow the rules, if we go in the counterclockwise direction, that's when we get a positive angle. All right, so now we have a different situation here in the next part. It says that when this student went, the center point landed 2 centimeters right and 3 centimeters up from the center of the spinner. So let's see if we can kind of model that. So here's the center of our spinner, 2 centimeters to the right and 3 centimeters up. What we could do is maybe plot a point here to show that's where the 2 centimeters is going to line up with the 3 centimeters. But we're thinking about our paper clip. And so if we were to actually draw in what that would look like, that paper clip is still centered in the middle. It's just going to look like a diagonal line pointing outward to that position. So here we're wanting to answer what angle did this student spin. So what we're looking for is the angle down here in that position. So our hint here is to draw a triangle on the axis. And we actually have part of our triangle already done. We can think of this diagonal line part as the hypotenuse. If we were to draw a vertical line straight down, sometimes I like to do this just with a little dotted line to like what looks like the x-axis, it seems that we've created the picture of a right triangle. And I'm going to make a couple other adjustments here. So instead of labeling those locations on the x-axis and the y-axis, I'm going to actually label them as the side lengths. So the side length going across the bottom here, like on the x-axis, would be 2 centimeters. And then this vertical length here that is going in the direction of the y-axis, that's going to be our 3 centimeters. So we're going to actually connect this with what we've been talking about all week with the right triangle trig ratio. So we're actually going to think about SOHCAHTOA here. So if we look at where our angle is positioned, it looks like we could label the side 3 centimeters as the opposite side. So it's on the opposite end of where the angle is. 2 centimeters is the adjacent side. If we wanted to set up a trig equation to solve for this missing angle, would it be best for us to use sine, cosine, or tan? We'll use tan. We've got the opposite side and we have the adjacent side. Perfect. All right, so we know from earlier in the week that the tan of some angle theta is equal to opposite over adjacent. Well, let's go ahead and fill in the pieces that we know. We don't know the angle, so we're going to keep it as a variable. We're going to keep it as theta. Our opposite side was 3, and our adjacent side was 2. Does anyone know how you can get the missing angle part? All right, it's a little function on your calculator. I'm going to show you. That's called inverse tan. We're going to take the inverse tan of 3/2, and that's going to give us the answer for our angle. So here's how this is going to look. So if you kind of think about doing the same thing to both sides, doing the same function on the left and the right, I'm going to actually put a little bit more space here before the 3/2. Here's what's happening. So it looks like a tan that has a little -1 up in the corner. And we're going to do more work with inverse functions as we continue to move through the semester. But that little -1 is a symbol of inverse. Just going to write that word off to the side here. And so on the left-hand side here, the inverse tan is a way to cancel out the tan. So that's how we're going to get our angle theta by itself. And so really what's happening, I'm going to rewrite this down below, is that if we're trying to solve for a missing angle on the other side, we're going to do the inverse tan of whatever the fraction was that it was equal to. So in this case, we're going to do the inverse tan of 3/2. Let's find where that would be on our calculator. So above your tan button, you should have an inverse tan symbol, and it should be in the same color as your second key. The way you know it's inverse tan is because it looks like a tan with a little -1. So we're going to get there by pressing second tan, and notice how you have a little -1 there. Now we're just going to type in 3/2, and the answer we get is our missing angle in degrees. It's about 56.3 degrees. So let me show you something here. So if that is the angle measure, that means that if we do regular tan, so I'm not going to press the second key, just press tan. If I do the tan of that angle, my answer should be 3/2. So let's try it. I'm going to type in that angle. I'm actually going to type in just as many decimal digits that I see. And if we do the tan of that many degrees, it equals 1.5, which is the same thing as 3/2. So let's go back here to our paper and see, okay, so that was about 56.3 degrees. And connecting it to like the original equation that we wrote up here, we checked it. The tan of 56.3 degrees was supposed to equal 3/2, which it did when we did our check in our calculator. Okay, so for this question, there's actually one more little piece that I'm going to write off to the side here that's going to connect this process with a slightly different way that your directions may be given to you for a problem such as this. So instead of the problem telling us that the spinner landed like 2 centimeters to the right and 3 centimeters up from the center, it might say something like this instead. Let the ordered pair, point 2, 3, be a point on the terminal side of an angle theta in standard position. So here's what that looks like in our picture. This point right here at the top of your triangle, if you think about this being on top of the XY axis, that's the point 2, 3. So the S value of the point is 2, so that tells us this length. The Y value of the point is 3. We can see that that point is sitting on the terminal side of our angle because the hypotenuse of our triangle, that's the terminal side. That's where our angle measure ends. In standard position, just meaning that the initial side is here. All right, one other little piece I want to point out here is that the center here of our picture, we do have a special name for that. That's the origin. Okay, when you're ready, we're going to go and turn over to the back. So we have 4 of them here. So we're going to squeeze them into our box. Here's how we're going to organize it. This is how I'm going to do mine. So I'm going to split it into thirds. And I'm going to make a little halfway section right there. All right, so let's take a look over at the whiteboard. So first learning target here was just to draw angles in standard position with both positive and negative angle measures. All right, so let's title this standard position. And this is just an angle that has a vertex at the origin, meaning at the center of that XY axis, and one side on the positive x-axis. So that is that starting point of our paperclip. That's the initial side. So when we say positive x-axis, this little position here where our paperclip starts. Let's other side is called the terminal side. Now, about the direction that it goes, we saw that if it was counterclockwise, it was a positive angle. And if it was clockwise, we get a negative angle. I'm just going to use this little symbol here to represent angles. All right, second learning target here is we wanted to find coterminal angles. And this is really just defined as angles in standard position that share a terminal side. And it's very easy to find them. We're either going to add or subtract 360 degrees. And you can do that as many times as you like. All right, learning target number 3. We used an inverse trig function to find a missing angle. So we did one example already on the front side. Another situation, let's say that we wanted to find the sine of some angle theta. Let's say that the sine is equal to 1/3. Well, the answer for finding that angle would be to do the inverse sine of whatever the whole thing was equal to. So the inverse sine of 1/3. All right. The fourth one here, so this is like what we did with the last problem on the front side. So here we're finding trig ratios for angles that are in standard position. So this is just connecting it back to the SOHCAHTOA work that we've done earlier in the week. So we're going to use the point given. So it's going to be given to us like in the form of an ordered pair, like x comma y. And with that, we're going to make a right triangle. And then solve for the angle. And that's where we did that inverse trig function button to help us solve for the missing angle. So a general example here of what the picture is going to look like. Our ordered pair, point xy, we want to start by plotting that point first. So say it looks something like this. And the way that we make it into a right triangle is we're going to start by drawing a diagonal line to the center. So every time I want you to think about your little paper clip, like what that means. The paper clip is always connected to the center. So that ends up being the hypotenuse for our triangle. So this is where we can draw that third little line down. I like to make it a dotted line to turn it into a right angle. Our angle theta is down here on the inside. And this measure of our triangle is really whatever the x value was of the point. And then this measure over here is going to be the y value. So there's a question in our check for understanding. There's another one on the blue homework sheet that's similar to what we're thinking about there in that last picture. Okay, so let's look at getting this next circle labeled. So we're still going to think about our initial side being along the positive x-axis, so the same place where our paper clip started. I'm going to go ahead and just label the first possibility of it being 0 degrees, so the paper clip doesn't move at all. And the first jump that we have here, that is the same size as the first section of our spinner today. That was 30 degrees. Now, to get to the next section of our spinner, we're actually going to skip over this line to get to our 60-degree label, and then we've got 90 degrees still at the top. So really the only thing that's new, the only thing that's different is we have this extra line that's in between the 30 and 60 degree mark. So how would we label that? Yeah. So it's halfway between 30 degrees and 60 degrees, halfway between 0 and 90. If you think about it taking 30 degrees and then divide that in half, it's really 15 degrees that we're going inward. So it's the 45-degree angle family that we're adding to this last circle. And so as you're filling the rest of these in as you go around, sometimes I think about the jumps that we're making. So I think, well, if it's a big jump, it's 30 degrees. But if it's a big jump, it's only 15 degrees. So see if you can follow that pattern to go ahead and label the rest of your page circle. Okay, so let's double check all of our labels there. So check to make sure that you haven't made a little calculation error in getting these. We have the same one from the spinner here in the second quadrant, but the one here in the middle is going to be 135 degrees. The new one that we're adding down here in the third quadrant should be 225 degrees, and then the new one over here is 315 degrees. So really just 4 new angles that we're adding to the ones that we had before. And then I just went ahead and ended at 360, again, just to show, well, if we continue, like if we made it one full time around the circle, that would be where we would land. Come back together. We're going to go through these 2 check for understanding questions, give you a little bit of feedback, make sure that you're on the right track before sending you off on your own for the blue assignment page. So we want to do the coterminal angle for the angle here that is shown. So we have 640 degrees shown, and you can see that's definitely bigger than 360. Showing up with the picture here, like we went around 1 full time, and then we went around quite a bit more, almost 2 full times, a little bit less so than that. So we're going to begin by finding coterminal angles, and the first requirement, the first one is to find something less than 640 degrees. How would we do that? We're going to subtract 360 degrees because we want a final answer less than 640. So we're going to subtract one possible answer here. There's a lot of possible answers when we're dealing with coterminal angles, but probably the most common answer we have in the room is 280 degrees. How can we find a coterminal angle that's bigger than 640? We have to add 360. And that's a fun answer. What does it get us to? 1,000 degrees. Okay, how can we possibly get to a coterminal angle that's negative? Oh, let's think about if we start back at 640 again. Well, if we subtract 360 one time, we get to 280, which is not quite negative yet. So we could actually just do it a second time. So you could either subtract 360 from 640 twice. You could subtract 720 from 640. You could subtract 360 from 280. These are all going to get us to the same end result of negative 80. And there's something kind of cool I want to show you here in the picture. Like if we were to draw this angle negative 80 degrees right here, so remember that negative angles go in the clockwise direction. It seems believable that this could be negative 80, right? Because negative 90 would get us all the way to the bottom, and this is a little bit less than that. So that would be negative 80 degrees on our picture. Okay, so coterminal angles are very easy to work with. Do you guys agree? Are we okay with these? add or subtract 360. That's it. Let's talk about the next one. So I had you change this to positive 8 so that we can draw our angle on the axes. I want the angle to be in the first quadrant. And there are some reasons for that. I just need you all to trust me on that, okay? So we're going to start with plotting the point. This is where I always like to begin, is just plot a point out in the quadrant. And when we're connecting that to the x and y axis, that point always needs to go straight to the origin. Because it's like the paper clip. So if you think about where the paper clip is, I'm going to use my ruler again here, starting here, like that's what that diagonal side is representing, and it's actually going to end up being the hypotenuse for our right triangle. So we can draw another line straight down here. This is where the right angle is made. Angle theta is always the one closest to the origin that we're dealing with. So this, what is this side line? Like how did you label that? That's the x value. That's 6. So what is this side line? 8. And what did you get when you solved for the hypotenuse? This is going to be 10. So this is just a Pythagorean theorem problem to get your hypotenuse. A squared plus b squared, 36 plus 64 equals 100. We square root that, and we get the hypotenuse of 10. So that's going to help us with part B of getting sine, cosine, and tangent for theta, because we can see 8 is opposite of theta, so that's like where our star is. 6 is adjacent. 10 is our hypotenuse. Okay, so here's something cool for part C. So here we wanted to determine how many degrees were in the angle. I'm actually going to write these out here in part B. This is what's going to help us answer part C. Opposite over adjacent. Okay, so all of these have a missing angle. We have the whole ratio part filled in. It's the angle theta that's missing. So this is where we're going to use our inverse. And guess what? You can do it 3 different ways. You can do inverse sine of 8/10. Look at what I wrote above. Or you can do inverse cosine of 6/10. Or you can do inverse tan of 8 over 6. And that missing angle, when you put that in your calculator, was it the 52.1? Yeah, okay. This little fact here at the bottom, this is only true. We have ultimate flexibility in the first quadrant. And that's the reason that I wanted both of those values to be positive. So if you haven't already done this, so here's my little reminder to you. On number 11 on the blue paper, I want both of these values positive. So instead of it being -3, 4, we want to keep that in the first quadrant, so it's going to be +3, +4. I have a digital copy of this that I uploaded to Schoology that has the correction made, if you forget. And it's not a huge deal if not, it's just sometimes we run into issues with this part. If you are continuing with pre-calc next year, you're going to learn a whole lot more about really going into depth with these inverse straight functions. That'll explain why it sometimes gets tricky when you're moving into different quadrants. Oh my gosh, it's 3:59 and you guys are still all here with me. That's wonderful. All right, make sure you have everything with you. You guys can go ahead and go. Have a great day. I will talk to you later.